Okay, students, welcome back. We're going to continue our notes with this measuring and calculating slideshow, and we're going to talk about scientific notation. Okay, this is a super important piece of information for you, especially in chemistry, as scientists deal with very large numbers, okay, such as the mass of the sun. So, the mass of the sun is this number in kilograms. That is a cumbersome number to write down, and you wouldn't want to do this very often, okay? Sometimes it's fun to see how many zeros there are to prove a point, but there are shorthand ways to write numbers down like this. So let's go over how to do that. In order to add zeros to a number, you simply have to use powers, okay? So 10 to the first power is going to be 10 times 1. And that equals 10, correct? 10 raised to the 1 power is 10. What about 10 squared? That would be 10 times 10, 10 by itself times itself. That would equal 100. Okay, I think you're going to see a pattern here. 10 cubed is 10 times 10 times 10. So it's 10 multiplied by itself 3 times, and that will be 1,000. And then lastly, here we have 10 to the fourth power. 10 times 10 times 10 times 10 would be 10 multiplied by itself 4 times. That will equal 10,000. Okay, so I hope that you see the pattern is the number raised to 10 is how many zeros you add to 1. Okay, so we have 10 to the first power. You have 1 0 to the right of 1. 10 to the second power, you have 2 zeros. 10 to the third power, you have 3 zeros. And 10 to the fourth power, you have a total of 4 zeros to the right of the 1. Okay, so this number up here, the mass of the sun in kilograms, would actually just be written this way: 2 times 10 to the 30th kilograms. Okay, so we have this 2 here. That is an important number to keep. So we have 2, and then we need to add the zeros. So to do that, we just take this 10 and raise it to how many zeros we want behind it, and that will be 30. And then don't forget your unit, which is in kilograms. All right, so it's simple enough. We're going to do a lot of practice on this, so make sure to wait for those things. Scientists don't just deal with large numbers, however. In chemistry, specifically, we talk about very small numbers. So the mass of a proton is this very, very small number. It looks large, but it's very small because the decimal is right there. Okay, so it's a fraction of a kilogram, a very small fraction. The way that you add zeros behind the decimal is through scientific notation again, and you use the fact that a number raised to a negative power will put that number in the bottom of the fraction, also known as the denominator. Okay, so 10 to the negative 1 is going to be 1 over 10. Okay, do you see that this 10 here raised to the negative 1 puts it below this fraction? Okay, so there's a 1 over 10 here. And this ends up being the decimal 0.1. Okay, so let's erase this so we have some space. And let's look at the next one. 10 raised to the negative 2 power will be 1 over 10 times by 1 over 10. Okay, and if you proceed with this calculation, you will end up with 1 over 10 times 10 is 100. And 1 over 100, of course, in decimal form, is 0.01. Think of this as 1/100th, okay, is 0.01. It's sort of like a penny out of a dollar, right? 1 penny is 1/100th of a dollar, and this looks like the way that we write 1 cent. Okay, so let's continue with this. I think you get the pattern pretty easily. 10 to the negative 3 would end up being 0.001, and 10 to the negative 4 ends up being 0.0001. So the trick here is that we're just moving the decimal as many places as the power tells us to. Okay, so if we have 10 to the negative 4, this is going to move the decimal to the left 4 places because this is a negative 4 up here. So 1, 2, 3, 4. You're going to move the decimal from 1 to the left 4 places to end up with your answer. Okay? So the mass of a proton is going to end up being this number. Remember, when you write in scientific notation, that you have to have a leading digit. Okay? So we see that the decimal is here, all the way over here. If we were to move it all the way back, we would see that there are 27 positions that we need to move it. And then we just take this number and we write it down. 1673. We need to have the decimal place behind the ones, and then you just add in all of the zeros. Times 10 to the negative 27. That's how many places the decimal moved over. And don't forget to include your unit. Okay, so it will be 1.673 times 10 to the negative 27 kilograms. Okay, which is much easier than writing it this way. I think you'll all agree. Let's do a little bit of practice to help this sink in. Okay, write the following in scientific notation. We've got 245 million. Okay, so how would we do this? We know that we need to have a leading digit, and we need to know how many decimal places we need to move this. Where's the decimal on this currently? Well, it's right there. It's right at the end. There's an implied decimal there. So we're going to need to move it 1, 2, 3, 4, 5, 6, 7, 8. So what we would do is write 2.45. And then the rest of these zeros, we don't want to write those every time. It's much faster to put this in scientific notation. 2.45 times 10 to the 8th. And that will be 245 million. Okay. It works the same way backwards with very small things. So let's look at this one. The decimal place is right here. Let's move it. Oops, sorry. Let's move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Remember that we have to have that leading digit. So this will end up being 3.4 times 10 to the something. Is it going to be negative or positive? Okay, that's the thing that you need to ask yourself. This one, in this case, it's going to be negative 11. And that's because a negative exponent puts it in the denominator, and that shows you that it's a small number. Okay, let's move on to letter C here. Where's the decimal on this one? Again, there's an implied decimal right there. Let's count these over. So 3, 6, 9, 12, 15, 16, 17, okay? So this will end up being 6.02. Those are the non-zero numbers. And then we've just got a string of zeros. So 6.02 times 10 to the 17th power will give us this number. So these are all equal to the original number. They're just written in a different form. All right, let's look at D here. The decimal is right here. We need to move it, 3, 4, 5, 6. We need to move it 6 to the right. So to represent a small number, we have 6 times 10 to the negative 6. Okay, remember that this has to be in the ones place to begin with. That's just standard notation. And lastly, let's look at E. This is also a small-ish number. We have the decimal here. We need to move it 1, 2, 3, 4, 5. Because we have to have a ones place, we have 1.4. And then we don't want to write the rest of the zeros, so we just tack on this last bit. 1.4 times 10 to the negative 5. Okay, and if these had units, you would want to tack on the units because we need to make sure that we always include those. Okay, if you need more help with this, just let me know. I will add more practice videos as well to the modules. Okay, let's finish this with accuracy and precision. Okay, we just need to be on the same page in terms of this vocabulary. Accuracy. Accuracy is the closeness of a measured value to a standard or known value. And precision is the closeness of two or more measurements to each other. Okay, so accuracy relates to things that we have a standard or known value and how close we are to that. And precision is how close multiple measurements are to each other. This makes more sense with an example. Let's look at this example here. This is something that you may see on a typical ACT question in the science portion. So let's go ahead and try to read this. Student density and error data is what we're looking at. The unknown was sucrose, and its density is given to us right there. Okay, we have student A, B, and C, and they each did 3 trials with an average included right there. Okay, they measured the density and their error each time. So the question is, which of these was the most precise? Which of these 3 trials? And which average was the most accurate? Okay, so precision has to do with the closeness of multiple measurements to each other. As we can see, student C had 3 measurements that were all very similar to each other. Okay, they didn't have a large range. Whereas student B had a pretty large range between 1.4 and 1.68. And then student A also had a larger range that went from 1.54 to 1.6. Okay, so student C here is going to be the most precise. And then the most accuracy has to do with how close you are to the expected value. We're given 1.59 grams per cubic centimeter as the known density of sucrose. So we just need to look at the averages and find the one that's closest to that. Student C was pretty far off. They were at 1.7. 1.51 is fairly close for student B, but 1.57 is the closest, so student A was the most accurate. Okay. Let's look at another example here. This is the stereotypical example for accuracy and precision. Let's look at a dartboard. Okay, we have 3 instances here where darts were thrown at a dartboard. In this first case, all of the darts are very close to the center, and they're clumped together. In the second case, we have a lot of darts that are clumped together, but they're not very close to the center. They didn't get a bullseye. And then in this last case, we have darts that are spread out and none of them are close to the center. So let's go through these and determine whether it has good accuracy and precision or poor accuracy and precision. Okay. In this first instance, we can say that it is accurate. Okay. Why is that? It's accurate because the goal was to get a bullseye. And it's precise because all of them are clumped together. There's not a lot of range. In the second case here, it's not accurate. Okay. There's very low accuracy here because they're far away from the bullseye, but it is still precise. Okay, you can have something that's precise but not accurate, of course. And in this last example, it is not accurate. That's obvious from none of them hitting the bullseye. And it is not precise either because there's a large range of where they landed. They're not clumped together in any spot on the board. Okay, so that's what I have as well here, and we'll pick up with the SI units next time.